Okay, now we're going to look at how to build a complex valued field as polarization. So how to modulate this, how to modulate our message onto polarization and make it propagate as EM wave. So this really is not as complicated as you may imagine, and this is really fun. We're going to build this up through examples. So first of all, we have the wave function, which is for the E field. So complex valued vector equals to E0. So this is a polarization. And then we have the wave propagation function I kappa z minus omega t. So the polarization is a complex valued field. So we have E0 complex value field equals to E0x. So x component, and then E0y, y component. And we have already proven that for EM wave there's no z component for the polarization. There is no z component for the E field. So the polarization will be on the xy plane. Okay, so let's look at the first case, where we have real and positive amplitude, and we only polarize in the x direction. So I have real and positive amplitude, and we only polarize in x direction. So first step is we express the wave equation. So I have E. Let's call it E1, because we are going to add different waves together. And then we have the amplitude E1, which is real and positive value for now. And then we have E I kappa z minus omega t, and then in the x direction. And then only the real part has physical meaning. So we have E1 equals to E1 cosine kappa z minus omega t, and then x direction. So only the real part of the wave function has physical meaning. So now, if you look at past exam questions, you'll see they often ask, give you a wave function and ask you to describe, temporal dependence of the polarization. So how do we observe the time domain property of this? We can observe it at any point, any location, any z. So we just set z equal to 0. Then this E1 would become E1 cosine omega t x direction. So what does it look like as polarization? So we have x direction, y direction. Suppose we observe this over 5 time instants. So I have T1, and then T2, and then T3, and then T4, and then T5. So the polarization is along the x direction. So we have at first when t equal to 0, this cosine omega t reach the maximum. So I have maximum along the x direction, and then it's reduced over time, and then reduced to 0, and then increase in the opposite direction, and then increase to the maximum to the opposite direction. So now, so t1 is 0. Any guesses what t5 is? It should be period divided by 2. So if it's full period, then we come back to the original point. So we come back to the peak again. Peak to peak is a period. But peak to half, peak to the opposite peak is half of the period. Okay, so this is what polarization in the x direction look like. So now let's look at another example. So case 2, we have still real and positive value for the amplitude, but we polarize in the y direction. So now the wave function we have, let's say we have E2. So this equals to a real and positive amplitude, and then EI kappa z minus omega t, the propagation function, and then we have y direction. And then the same as before, only the real part has physical meaning. So the real part is given by E2 equals the amplitude and then cosine kappa z minus omega t and then y. So if we observe its time domain, amplitude dependency, we have z equal to 0, and then this function becomes E2 equals to an amplitude E2 and then cosine omega t and then y direction. So what does this polarization look like? So I have x and y. So now we also observe this over 5 time instants: t1, t2, t3, t4, t5. So now polarization is in the y direction. So when t equal to 0, we reach the maximum in the y direction, and then it's reduced, and then it's 0, and then it's increased to the opposite direction, and then it's increased to the maximum in the opposite direction. And then we have, assume we have, let's see another case 3, which is going to be a more general case, where we define a E3. So this equals to AE1 plus BE2. So E1 is polarized in the x direction, E2 is polarized in the y direction, and with some ratio, and we add them together, E3 will be polarized in both x and y direction. So we have, AE1 x direction plus BE2 y direction, and then EI kappa z minus omega t. E3 looks a bit more complicated. So before we make it too complicated, let's look at some simple examples of E3. So I have case 3.1, where we have A equals B equals to 1. So we have, for this case, we have E3 equals to E1x direction plus E2y direction, and then EI kappa z minus omega t. Okay, so that's a wave function. And then only the real part has physical meaning. So we have E3 equals to E1x direction plus E2y direction, and then cosine omega t, cosine kappa z minus omega t. So at z equal to 0, what do we have here? We have E3 equals to E1x direction plus E2y direction, and then cosine omega t. Right, so what does this look like? We have polarization on the xy plane, and then we observe this over 5 time instants. So here, if E1 equals E2, then at time 0, we have equal magnitude on the x direction and the y direction. So this is a diagonal vector. And then it would become smaller, and then 0, and then increasing in the in the opposite direction, and then increasing to the maximum in the opposite direction. It's kind of a diagonal, direction. Okay, another example. We have A equals 1, and then B equals minus 1. So what do we have? We have E3 equals to E1 x direction minus E2y direction, and then EI kappa z minus omega t. So if we look at the real part only, we have E3 equals to E1 x direction minus E2y direction, and then cosine kappa z minus omega t. So now at z equals to 0, we have E3 equals to E1 x direction minus E2y direction, and then cosine omega t. So this polarization will have x, y plane, and if I have E1 equals E2, then we also observe this over 5 time instants. We have T1, T2, T3, T4, and T5. So So now when t equal to 0, we have both of them equal amplitude, but x component is positive, y component is negative. So it is this way, and then it is reducing, and then become 0, and then increasing in the opposite direction, and then increasing in the different direction to the maximum. So it's kind of anti-diagonal polarized. So let's now look at more tricky applications. So we have case 3.3, where we have a equals 1, and then b equals I. Okay, so now we will have complex valued polarization. So now E3 will equal to E1 x direction plus I E2 y direction, and then EI kappa z minus omega t. So now the polarization is complex valued and its field still x direction, y direction. So now the real part we have E3 equals to, so only the real part. So here x direction we have real part. So E1 will multiply cosine part of this complex function. And here we have the imaginary part. So this must multiply the imaginary part of this function. So, and also I multiply I give us -1. So we have, first we have E1 cosine kappa z minus omega t, and then minus E2 sine kappa z minus omega t. Sorry, this is x direction, this is y direction. So here we have I multiply I sine the phase. So I have minus here, I multiply I. Okay, so now at z equal to 0, what happens? We have E3 equals to E1 cosine omega t x direction plus E2 sine omega t y. So y plus, so here z equal to 0, I have minus here, sine minus a phase equal to minus sine of the phase, and then here I have minus, so positive. Okay, so what does this polarization look like? So I have x, y, and also if E1 equals E2, then we observe at T1, T2, T3, T4, and T5. So when t equal to 0, we only have the x component, we don't have y component. I start from here, and then afterwards I'll rotate a circle. You see, when we only have y component, we don't have x component. That is, t divided by 4. So this is t divided by 2. This is t divided by 4, and this is 0 for the time. And then we have here, and then here. So it's kind of anti-clockwise. So this is also called anti-clockwise or left circularly polarized. So this is a very classic example. And now one more example, we have case 3.4. We have A equals 1, B equals minus I. What do I have? So I have E3 would equal to E1x minus I E2y. And then we have EI kappa z minus omega t. So the real part, we have E3 equals to, real part we only have, it's not complex value anymore. Then we have E1 cosine kappa z minus omega t x direction. And then here we have this term multiplied the imaginary part of this function. So this would give us positive E2 sine kappa z minus omega t y. Right? So minus I and then I sine. So here. Then at z equal to 0, we have E3 equals to E1 cosine omega t x minus, so here we have z equal to 0, so we have minus sign here inside of sign, we put it out, we have E2 sine omega t y direction. So now we can see the pattern already. So the polarization here, if we have E1 equals E2, then time T1, time T2, time T3, time T4, time T5, we have at the beginning, when t equal to 0, we have positive maximum towards in the x direction. And then when we have small value, then it's positive in the x direction but negative in the y direction. So this would rotate this way, and then this way, and then this way, and then this way. So it becomes clockwise. So we call it clockwise left, right circularly. Here, like this. So right circularly polarized. So now, the earlier example here, earlier 4 examples, they are all linear polarization. So for example, this one polarized in the x direction, and then the second one polarized in the y direction, and then third one polarized in diagonal direction, and the fourth one polarized in anti-diagonal direction. So these are all linearly polarized. But the more complex ones here, they are circularly polarized. So if you put all this together on this plane, you have all the points on a circle possible. So if you start from here, it will go anti-clockwise. And then here, this one is also a circle, but it's clockwise. Now what happens when E1 doesn't equal to E2? So we have, for example, a past exam question where the field is expressed in this way. So E equals to E0, and then exponential function I kappa z minus omega t. And then the polarization direction is expressed as x plus j2y. So here, in terms of the sign, it's the same as, anti-clockwise polarization or left circular polarization. If you see this on xy plane, what you will see is when y component, so this is in the same format as this one, but E2 is higher, so I have E2 equals 2E1, which means when we don't have E2 at the beginning of t, we have x here, and then on the y direction, when we don't have x, we have here E2, so this is E1, this is E2, and this is no longer like a circle, but an ellipse. So the polarization start from here, it will go, anti-clockwise. So it will be an ellipse, and then you can extend this to, time domain observations. What do they look like? Actually, this one here. Okay, but the amplitude would change, not like this one. This is circle, and this one would be ellipse.